This training module describes methods used to estimate drainage areas. The drainage area is important because it controls the flux of water through the basin in a given region. The precipitation and prestorm flows are multiplied by the drainage area of the highway site and the upstream basin to calculate storm flows. This is training module 2.04D for the Stochastic Empirical Loading and Dilution Model SELDM. This presentation has 14 slides and will take about 9 minutes. It was prepared by the U.S. Geological Survey in cooperation with the Federal Highway Administration. This training module has 4 learning objectives. At the end of this module, you should be able to describe the drainage area and its importance, discuss issues of concern for delineating drainage areas, identify tools available for estimating drainage areas, and discuss the accuracy of manual delineation methods. The basin drainage area is defined as the river basin area projected onto a horizontal plane and enclosed by a topographic divide so that the direct surface runoff from precipitation normally would drain by gravity into the river basin. This image shows our hypothetical basin with the area in gray. The projected area is used because that, by and large, defines the local flux of precipitation into the basin. In some areas, the groundwater and surface water divide may not be the same, which will affect the amount of groundwater discharged to the stream. In some areas, particularly in small basins and at highway sites, storm sewer drainage systems may divert storm flow from one topographic drainage area and divert it to another. Use of topographic contours of about 2 feet and manual inspection of drainage basins may be necessary to delineate basins on the scale of a city block in areas with storm sewers. Difference between natural topographic divides and anthropogenic divides can be substantial even in relatively large urban basins. For example, researchers noted that sewer drainage delineation for Malice Creek in Michigan more than doubled the drainage area from about 3.9 to 8 square miles in comparison to topographic divides. In another study, researchers used GIS coverages to delineate small urban catchments, and they discovered substantial differences in drainage areas greater than 20% in 17 of 18 basins on the basis of differences between expected and measured median runoff coefficients. In that study, differences as large as several orders of magnitude were confirmed by obtaining detailed drainage plans and doing site inspections. However, we will only consider the more common case for many basins in which the topographic divide is sufficient for our initial estimates. In very small catchments, temporary changes in drainage area may be caused by clogging or surcharging of drainage inlets. This image from Route 2 in Massachusetts indicates how sediment and debris can dam up a storm drain inlet to cause bypass flows. When we do SELDM models, we must ignore such transitory effects. However, the population of runoff coefficients used to model runoff in SELDM probably include the effects of such processes. This is a planimeter, which is a tool that can be used to measure areas. To use a planimeter, one arm is fixed in place, and the other arm, which is shown as the arm on the watershed outline in the image, is used to trace an area. The gears on the planimeter provide measured area that can be scaled to the actual area of the basin. Planimeters commonly were used to measure areas when drainage areas were drawn by hand. Planimeters are still available for purchase and are in use. However, most watersheds now are delineated and measured with computer applications. The USGS Streamstats application provides an easy and robust method for estimating drainage areas. This image shows the online Streamstats viewer. Streamstats provides good drainage area estimates because it uses manually derived watershed boundaries as its base, and it uses the digital elevation data to delineate the watershed between the point of interest and the nearest predetermined watershed boundary. To get the drainage area from Streamstats, zoom in, click on the stream with the Basin Delineation tool, and then click the Basin Properties tool. This image shows the Streamstats delineation for Howard Brook in Massachusetts. The yellow area with the black boundary is the drainage area above I-290. Streamstats estimates can be obtained in most states. This is a map showing the status of Streamstats. The pink areas are multi-state basins. The green states are fully implemented in Streamstats with basin properties and regression equations. The purple states have delineation and basin characteristics only. The blue states are currently undergoing implementation, and the yellow states are not participating as of early 2020. In early 2020, Streamstats was available in 40 states and was being implemented in 4 states. The drainage area is universally available in all Streamstats applications. The Adobe PDF measuring tool is the poor man's GIS. It is a distance tool and an area tool that can be used to delineate and measure areas in PDF files. The USGS has migrated the topographic quadrangle maps to geographically enabled PDF files that you can use. This image shows a PDF file output from Streamstats and measured using PDF measurement tool on the left, and the toolbars and output formats for the tools on the upper right. The top right bar shows the measuring tool with the area option selected. Once you select this tool, you click the mouse around the area to be measured. The area tool window provides a running total estimate, and the results are inserted in a sticky note annotation when you are complete. The middle right bar shows the measuring tool with the distance option selected. Once you select this tool, you click the mouse at both ends of the distance to be measured. The distance tool window provides the distance, angle, and change in the X and Y direction. It provides a dimension line like the one shown below on the map scale when you are complete. Dot plot or grid paper may be used to estimate basin areas from paper maps. These map overlays are transparent and commonly are proportioned to different map scales. When you use a dot plot overlay, you count the intersection points within the boundary rather than trying to estimate partial grid square areas. In theory, finer grids produce more precise estimates, but counting large numbers also may introduce errors. There are 30 points in the coarse grid and 752 in the fine grid covering this hypothetical watershed, which result in estimated areas of 14.47 and 14.5 drawing units respectively. The actual area is 14.6 drawing units. Therefore, the grid estimate errors are both less than 1%. The area sampling method produces surprisingly good estimates. To generate an area sampling estimate, draw a line or lines up the center of the watershed. Then draw perpendicular lines at regular intervals. Measure the center line and the perpendicular lines. Multiply the length of each perpendicular line by the distance between the lines and sum the areas. Finally, convert your measurement scale to the scale of the map to get the area. The sampling area for this hypothetical watershed is 15.2 drawing units, and the actual area is 14.6 drawing units. The difference of about 4% is within the national standard of 5% for delineating watershed areas. Some drainage basins cannot be estimated using a single center line. This image shows the Streamstats watershed delineation for the unnamed tributary above Route 17 on Pinto Mesa, Arizona. In this case, two center lines are needed to estimate the area with the sampling method. In this figure, the center lines denoted as L1 and L2 are used to facilitate measurement of two almost perpendicular sections of this watershed. The third line, which is perpendicular to the end of line 2, is the dividing line between areas. On this map, length 1 is about 0.87 miles, and length 2 is about 0.55 miles long. The next step is to draw perpendicular width sections labeled as line W1 through line W9 on this map. To calculate the average, either multiply the average width times the length or multiply each width times the associated proportion of the length and sum the results. In this training module, we learned that the drainage area is the map area and not the land surface area of the basin. There are two main issues of concern for delineating drainage areas. The issue of concern for estimating drainage areas to calculate pre-storm flows is the potential for differences between surface area and groundwater divides. The issue of concern for estimating drainage areas to calculate runoff is the difference in drainage areas caused by storm sewer routing. You may use a planimeter, GIS, Streamstats, the Adobe PDF measurement tools, or dot or grid overlays, or the sampling method to estimate watershed areas. All of these methods, if used carefully, can produce drainage area estimates that are within a few % of the actual drainage area.